All right, so I want somebody else to share their screen. I want somebody else to share their screen so that we can take the next question, the next example. Anyone else? Anyone want to share their screen? All right, so I'll keep going. If you change your mind, let me know. So if you remember the first approach, we said we used a code that just had LM. Okay, LM. We can also model linear mode. We can also do linear regression using this function, GLM function. And the reason why we are introducing this GLM function to you is because this GLM function becomes more important when we get to like logistic regression. In logistic regression, you have to use this GLM function. I will look at logistic regression next week, right? Essentially, these models that these linear models that we're doing, linear regression, logistic regression, and others, they have the same structure of the code as well as of the statistics behind them. Okay, they have the same structure, and then we just make small changes to the structure of the model to allow us to implement it in a specific way. Okay. Now, this is the code to implement the GLM. Okay, and so if you do it, and a lot of the coding is fairly similar. Especially here, you have the response model, you have the response variable, here you have the predictor variable, you have the data. Okay, but in this case, you're going to have to specify the family. The family is the group of models that you're including here. And here, you're using Gaussian. So Gaussian is basically normal regression, a normal distribution, right? So we're assuming that these variables are normally distributed. And then the link is identity, okay? I'll explain this identity when we get to logistic regression. You'll see how it differs. So in this case, let's just take it as it is for now and move forward, okay? So when you run this model, you get a model that looks fairly similar to the first one. The estimates are the same because they're doing the same thing. The p-values are the same. It's just the way that we have written the code that's different. Questions?
Where did we get the data RDS? What's the RDS?
Is the resident doctor's fund.
Okay, so how do I bring it into play? Am I supposed to open it?
You're supposed to read it in here.
Okay.
Yeah, so we read it in much earlier, and we've been working with it. That's why we didn't read it in a game.
Okay.
Yeah, so if you scroll up to this example 7, that's where you'll find it.
Yeah.
Okay. So in example 8 now, we have shown you 2 ways to implement linear regression. Okay? Any questions? All right, so let's get going. So if you remember in class last time, Ebua was talking about how after you do the model, you can assess the goodness of fit, right? And that's essentially what this is. Basically, you're trying to evaluate the models to see whether, the extent to which our assumption that this is to see whether our assumption that this is normally distributed data holds, whether we're doing this correctly. Okay. So this is the code that we use to essentially just ask R to plot the model for you. It's the same model. So one of the reasons why we do this, we name the model, right, is because it gives us flexibility to do something like this, where you can just ask R to plot the model for you, and then when you ask R to plot the model for you, this is where you get the residuals versus the fitted. You get a number of graphs, and this is one of them. And if you remember in class, who remembers in class how we're supposed to interpret this? What are we comparing this red line to? Anyone remember? Anyone?
I think this is like putting up a box plot.
It's not quite a box plot. It's more like a scatter plot in the sense that.
Yeah, a scatter plot.
Yeah.
That line 0.
Okay.
It's kind of dividing the two sides. And then if you notice, there's negative below, and then there's positive above.
Yeah.
Yeah, so basically, everyone that is negative, like we said, is negatively correlated, and then those above are positively correlated.
Okay. So that's an interesting line of thought. But what we actually do here is that, if you remember, we are doing linear regression now, right? And we have run this linear regression model. So we are taking this model and we want to go behind the curtain to see what's going on. That's really what we're doing here. So these numbers that you see here, they're not the true numbers that we put into the model. They are predicted values. Okay, so predicted values are basically, let me go back here and explain this to you. Okay, so here, if you look at this person who worked 60 hours, right? And their mental health score is 27 something. Now, if you run the model and you're able to get something that looks like maybe this, and then the mean, which is the intercept, remember this intercept that we talked about, is 26.35. And we said that this 26.35 is the mental health score for somebody who didn't work any hours, where the hours worked is 0. Okay? So in this case, that means somebody this person is not even on this plot, but that person's hours worked is 0. So if you have somebody who worked 40 hours, we can multiply this by 40. Okay, and so we'll get maybe minus 0.12, and we add that to this, we'll get a predicted value. The predicted value is the number that you would get if you were to guess, right? If somebody gave you the intercept and the hours work, the better estimate the intercept and the number of hours the person worked per week, which is 40 hours or 45 hours. If you're going to guess the mental health score of that person, that's the predicted value. Let me explain that again. Somebody gave you this regression model output, right? And they told you that what is the mental health score for somebody who worked 40 hours. Okay? You can multiply that 40 by this beta estimate. Okay? and then add that to this number, and that gives you a guess of what the mental health score of that person who is likely to be the person who worked for the hours. That's a predicted value. So we can then predict, we can look at the predicted value. So for somebody whose predicted value is 23.0, this is how far that person is from the mean. If for somebody who's, whose predicted value is 24.5, for some of them, one person is actually far from that predicted value from here, from here, from here. So you have this plot that you then generate from the predicted values for each individual in the population, in the sample, okay? And then you compare this plot to this outline to the line, to this zero line. That's all you're interested in this plot. You want to see how far away this red line is from zero. Okay? Let me explain this again. And I will not go all the way to explain what the predicted value is. Assuming you already know how to obtain predicted values, what R is doing here is that it is plotting the predicted values against the residuals, okay? And so it's essentially an estimate of how correct you think your model is, okay? And you expect that a perfectly done model will have a red line that is horizontal along zero. This model is not perfect, but it's close enough, and that's why this red line is not too far from zero. Okay. If you go back to the video to last week's class, if we were explaining this in more detail, but I hope this is good enough. And I hope I didn't confuse you further.
No, it's okay.
Okay.
Good enough.
Anyone else? Anyone else? Yeah. What do you say?
No, we're good to go.
Okay, excellent. All right. So the next thing I wanted to see is to show that we can use. So if you remember in the first one, this hours work is a continuous variable, but sometimes you can also use binary variables as predictors. And that's the first thing that you do here is that you create the binary variable. Okay. You need dplyr. Dplyr is a package in R that you use for data management. Dplyr allows you to have this pipe. This is called the pipe operator. Okay. There's one of the most important things I wanted to point out is this line. Okay. Sometimes when you're creating code in R, most people will just do this one where you specify if hours worked is more than 80, then the new variable will say 1. If it's more than, and this is a mistake, this should be 70. Then the new variable will say 1, otherwise it will say 0. Okay. So, but what if you have missing variables? This is always important to preserve the missing variables that come with the data and then to use formal approaches, statistical approaches to try to address it. Okay. So if you're going to create a variable, a dichotomous variable, this is what you will do. So if you run this code, now if you look in the RDS data set, you will find this new variable, this one at the farthest end. R is greater than 70. And if you see this person's hours worked is 50, so that is 0, 70, that is 0, 50, that is 0. But if you see this person's hours worked is 80, so that is 1, 72, that's 1, 71, that's 1, okay? So the code worked on fine. And we can then use that. I think I went too far. So we can then use that hours greater than 70 as our predictor variable. So here we first of all run the same model to show you. Okay, and then if you run the model with hours greater than 70, you'll find that this is the result. Okay, so who can interpret this linear regression for us? Anyone want to try? Anyone want to try? We'll just wait, or if we don't get any volunteers, all of us will just wait here, and then once it's time to close the class, get up and go. Someone says inverse relationship. Okay. With high strength of 0.9, it sounds like you're interpreting linear regression the same way that we interpreted the correlation score, but that's not exactly the way to interpret it, because this is not the same thing. A linear regression is not the same thing as a correlation. A correlation goes from -1 to 1, right? The highest is 1 and the lowest is -1. So if you have a correlation of -0.9, that's the strong negative correlation. But for linear regression, this beta estimate can go above 1. It can be 24, it can be 27, it can be 300, and 1,000. Okay, so it's not the same way that we interpret it. But you're right that because it's a negative sign, that is an inverse relationship. So that is correct. Okay. But how do you interpret this number?
From what you said previously, can you hear me?
I can hear you, yes.
From what you said previously, you said for every 1 increase in the hourly work,
Yeah,
it means there's an increase of 0.962.1.
in the mental health score, right?
That's correct, yeah.
Exactly. But because you remember the last variable that we looked at, hours worked, was a continuous variable.
Yes.
So that means that it went from 40, 41, 42, 43, up to 50s, 51, all the way to 100, right? So you can interpret that as for every 1 unit increase for every 1 hour extra work. But because this variable is a binary variable, it's just 0 or 1. You are either working greater than 70 or not. If you're not working greater than 70, that means you're working less than or equal to 70. Okay? So if you're going to interpret this, you cannot interpret it as for every 1 extra hour work. So do you want to try again?
Yeah, so do we now take it that, like you said, it's a binary variable?
Yes.
And it means it's either a true or a false. So if it is less than 70, it means it's a false.
Correct.
And if it is greater than 70, it means it's a true. So in variable, what it means is that since it is negatively correlated, negative linear regression, it means that if you look at this is a very high, how do I put it, 0.96, it means there's an increase of 0.96 for every variable that is less than, for every hourly work that is less than 70. I think I'm trying to like.
You're very close. Yes, you're very, very close. And this is an excellent attempt. Okay, so let me explain. Essentially what this means, remember we said the intercept. Okay? The intercept
Yeah.
is the estimate that you get when this guy is 0. Okay? The intercept is what? The estimate that you get when hours greater than 70 is 0. And remember we said hours greater than 70 is either 0 or 1. Okay? So what this means is that for people who work less than or equal to 70, that means people who did not work greater than 70 hours, their mean mental health score is 24.1974. Okay? But if you work greater than 70 hours, that means that for that person, this variable is 1, right? Then this is the increase, or this is the change. Okay, this is the what? The change in mental health score that you get. Let me explain that again.
So it means that the change is so small. I mean,
Correct.
towards it.
The change is so small. Very good. So it's basically a change of one basically. Yeah. Right. And it's a reduction. That's why you have a negative sign. Yeah. Okay. And that's why you can also see here that this p-value is not significant. Okay. So the change is so small, it essentially says that it's hours greater than 70 is not a real important, is not a significant, is not a significant predictor. And it's not, it might not be an important predictor because the magnitude of the effect that it is having on the mental health score is not large. Does anybody else want to maybe say if they agree or disagree with that point? Or if they still have questions about it? All right, let's keep going. And this time, the next one that we're going to do, I'm going to call people, multiple people, to give it a shot to explain it. Okay? So get ready. All right, so the hours work variable, the same variable, in the last example, we made a binary variable out of it. But we can also create a categorical variable out of it where it has 4 levels or multiple levels, 1, 2, 3, 4. Okay? So we can create multiple levels out of the same variable. And then we have a categorical variable. So if you run this variable, and if you look in the data set, you have a new variable, hours category. And so 1, 2, 3, 4 different people have different, depending on how many hours they work. So if they work less than 40 hours, less than or equal to 40 hours, that is 1. That's the lowest. If they work between 40 and 60, that is 2. If they work between 60 and 80, that is 3. If they work more than 80, that is 4. Okay? Do we understand the way this variable is set up?
Yes.
Okay, excellent. Anyone have questions about it?
Can you take it again?
Okay, very good. So in the first line, we say that anybody who does not have the variable hours worked who is missing, then R will specify NA. Okay, that's missing. Now, if they worked less than or equal to 40 hours, in the new variable that R will create, this is the new variable, R start, that variable will be 1. If they work between 40 and 60, okay, that variable will be 2. If they work between 60 and 80, that variable will be 3. If they work between greater than 80, then that variable will be 4. So this 4 is essentially saying whatever is left will be 4.
Basically, that's a categorical.
And that's categorical variable. Excellent. Okay.
Yeah.
All right.
Yeah.
So